Okay, so welcome everybody to today's special year seminar on theoretical machine learning at the Institute for Advanced Study. Today we are delighted to have Dr. John Langford as our speaker. John is a partner research manager at Microsoft Research and is known for his fundamental contributions to online learning, reinforcement learning, and unsupervised learning. Among his best-known contributions are the co-inventions of ISOMAP for dimensionality reduction, cover trees for nearest neighbor search, conservative policy iteration for reinforcement learning, and the modern CAPTCHA. He served as the president of the International Machine Learning Society, the general chair and program chair of ICML, and is an editor of the book on scaling up machine learning. Today, John will tell us about latent state discovery in reinforcement learning. Please welcome John Langford.
Thank you. This is about a research project that I've been working on for several years with many other people. We're trying to come up with essentially a new foundation for reinforcement learning. And I'm going to try to relate what we've discovered and maybe give you some ideas about how to further understand reinforcement learning in general. All right, so thank you again for inviting me, and you should feel free to ask questions during the talk. I'm just trying to cover the gist of things rather than going into the super deep technical details. So we should have time to answer questions, and I would like to answer questions just to understand where people are in terms of understanding what I'm discussing. Okay, so let's start with reinforcement learning. Let's think about what reinforcement learning is for just a moment. So you have a world and you have a reinforcement learning agent, and some observation comes from the world to the agent. You have a policy in the agent which needs to make a decision about which choice to take. It chooses some action, and then another observation comes from the world. You have a policy which needs to make a decision again, and then there's some action, and then maybe finally you get some reward. And in general, you may have many different observation action pairs before you actually see the reward at the end. Or maybe you have intermediate rewards as well. There's many different alterations to things. So I think most people don't need to be convinced about reinforcement learning, but I think the fundamental thing here is that this is just a very fundamental natural problem. Very, very basic animals, like very low level worms, can learn to do reinforcement learning. And at the same time, there's a lot of interesting complexity that arises in trying to do the more complex forms of reinforcement learning. So one of the things that you want to do when you're thinking about how to solve reinforcement learning is to think about how can you decompose reinforcement learning into sort of a set of orthogonal problems, and so that you can kind of concentrate on them individually and solve them, and then recompose them in order to solve the overall problem. So there's a set of three which I think about. One of these is credit assignment. So this is essentially which move lost the game or which move won the game. So it's often not clear exactly which action in a long sequence led to you winning the game. And then another one is exploration. So an exploration, I think, has a kind of a vital definition in the sense that often in order to learn effectively, you have to gather the information from a regime which is relevant to what you want to learn. So exploration is about trying to find information which is necessary in order to learn effectively. And then the third one is generalization. Generalization is very familiar from supervised learning. So in supervised learning, you need to learn to predict that, that's a road and those are trees and that's the ground, based upon experiences which are just different from what you're actually observing. So you never actually see the same image twice, and yet still you need to learn effectively. So these are what I think of as kind of the three core problems in reinforcement learning. And if you think about these core problems in pairs, there's actually pretty good solutions. So if you're doing generalization and credit assignment, you're trying to solve policy optimization. The solution to go that the DeepMind folks worked on is, I think, a good example of policy optimization as a strategy to solving problems. And then if you're trying to solve generalization and exploration together, that's really what contextual abundance is getting at. So in contextual abundance, you're just dealing with sort of the immediate one-step reward. And maybe the most canonical form of this right now is this personalized service, which Microsoft has put out, which essentially gives you a general purpose contextual abundant interface. You can send in features, you can get back an action, you can tell it a reward, and it will just learn in the background with a live model. And the third one is more of a toy of the theory folks, but it's MDP learning. So it started with the E-cubed algorithm way back when I was a graduate student. And since then, people have greatly improved things, and they have many new views about how to best learn in a markup decision process. And the general idea here is often something where or a canonical version of this idea is something where you're building a simulator of the world based upon the experience that you have, and you're using that to kind of plan to reach new regions so that you can explore and discover new things. So these are kind of the three key problems. Each pair of them is fairly well solved. And so the natural question is, can you actually solve all three of these? And this is a diagram which I think is fairly informative if you think about it carefully. So if you figure out how to add global exploration to policy optimization, then maybe you're getting at those question marks. Or if you figure out how to add generalization to MDP learning, then you're figuring out how to get at these question marks and so forth. So what I'm going to be discussing here is an approach to try to solve all three of these together, or maybe a family of approaches to try to solve all three of these together, which involves latent state discovery. Okay, so what is a good example of something which is like a problem which it kind of exercises all three of these difficulties at the same time? And I think a good example to think about is a navigation task. So you're in a new house, something comes up, you need to go to the bathroom or the kitchen or something like that. How are you going to actually get there? You have a state, you have a particular location that you're at. You have what you see, which is a very rich sensor space in general, much richer than your actual location inside the house. And then you can make decisions where maybe you go forward or maybe you turn to the side, and that changes your state. So you kind of have to deal with the fact that actions are changing where you are in the house very directly. You have to deal with the fact that you're seeing something that you'll never see again. So it's a generalization problem. And you need to actually explore in order to discover where the bathroom is or where the kitchen is or wherever you want to go. So all three of these problems are kind of exhibited in this navigation application. Okay, so now it's important to think a little bit about what's hard here. And there's a basic loop that comes up where you need a good policy to collect good data. You need to have a way to decide where to go so that you can discover new information. And then you also need to have good information to figure out where to go. And so you have this kind of loop here, which makes it kind of challenging. So I'd like to stop for a moment and ask if there are any questions about this so far. So you have this chicken and egg problem around getting data and finding a good policy. You have canonical problem where you really need to address all three aspects in order to solve things well. And then you have all three aspects together which I think define a lot of what we consider as advanced reinforcement learning applications where we don't necessarily know how to solve things effectively. Are there any questions about this?
Yeah, so we have one question from Kishan. The question is, because POM-DPs are considering context, would you consider that to be looking at all three problems mentioned?
Yeah, so POM-DPs are kind of, I think of POM-DPs as not MDPs, basically, in the sense that you are observing something which is not simple. So if you say, I have a POM-DP, you're saying, oh, things are not simple. And that is challenging to solve in general. We're certainly looking into situations that you could call POM-DPs, but they'll have extra constraints, which makes them solvable. So that's kind of going to be so the question in my mind is, what are the natural structures in the world which allow us to define a new class of solvable problems, richer than standard MDPs, rich enough to actually capture all three of these problems, but still with enough structure so that they're actually solvable in practice.
Thank you. The next question is from Mike. The question is, can we use priors for policies and data?
So priors in general can be used, and priors are not a part of the focus here, but one way to think about priors is structural priors, right? And it's very natural to create structural priors for the kinds of problems which end up being tractable to solve.
Great, thank you. The next, so we have two more questions, and then I think we'll move on. So the next question is from Pawan. Can you please elaborate on what good data means? Is it in terms of credits, assignments, or generalization, or both?
Yeah, so good data is the data which is necessary to solve a problem. So if you are trying to solve Go and the data that you have is generated by some process that is completely unrelated to the task the opponent you're going to face, then you may have difficulties when you actually face an opponent who's generating data that you've never observed before. Another more extreme example of this is that people have played around with some of these solutions to video games. And you can do seemingly completely innocuous things which destroy the quality of a learned policy. So if you have like a Pac-Man game or something, you can change the shape of one of the pathways, and suddenly the system can just fall apart. So that brittleness is partly about having the wrong bias, but it's also just about whether or not you have the data for the kind of problem that you're trying to solve.
Thank you. And the next question is from Anna Thomas, who has a high-level question. Does a similar kind of chicken and egg problem arise in other settings? And can we draw any insights from those?
Yeah, so I think often it does arise. And I think the relevant insight is that often you can unwind things step by step. And that's actually what we're going to take advantage of here.
Thank you. Those are all.
Okay, so I'll go on a little bit. So I want to first discuss some approaches to solving this problem that are not going to work in general, just to help exercise your intuition. So one of these approaches is using an autoencoder. So the idea here is that you have some sort of high-dimensional observation. You're going to send that high-dimensional observation through a bottleneck, and then you're going to try to generate the high-dimensional observation given the bottleneck. And the failure mode of this approach is that, so maybe you have one state bit. So do you see my mouse?
Actually, no.
No.
Okay.
Let me,
Okay, now I do, yes.
Oh, you see my mouse, okay. So, so maybe you have a one state bit, which is describing the world. Then you have a whole lot of noise bits. If you train your autocoder to minimize the log loss of reconstruction error or something like that, then it turns out that you can reduce your entropy or your log loss by just echoing a noise bit. And it's actually superior to echoing the state bit if the state bit has less entropy than the noise bit. So this kind of approach can just be distracted by noise, and you end up just kind of creating a definition of state, which is the low dimensional bottleneck, which doesn't have any bearing on the dynamics of the world. So another approach which people have looked at is trying to predict the previous action through a bottleneck from the previous and current observations. So this is the curiosity-driven exploration approach. And there's a counterexample here. I think it's worth walking through carefully. So in this counterexample, what happens is you start randomly in either S1 or S2. You don't know which. So it's 50-50 between the two. So given S1 and S2 and S3 and S4, so you can predict that the action taken was action 1. So you can always predict perfectly. So you can satisfy this prediction problem with 0% error. And then given either S1 or S2 and either S5 or S6, you can predict that the action taken was action 2 perfectly. So you can satisfy this prediction problem perfectly. And then we can do this again. We can say that given S3 and S3 or S4 and S7 or S8, we know that action 1 was taken. And so we can predict that perfectly. And then given S5 and S6, S5 or S6 and S7 or S8, we can predict that action 2 is taken with a 0 error. So we have 4 prediction problems which we solve perfectly. And so what's going to happen is this kind of approach will kind of alias S1 and S2 as a single state, and S3 and S4 as a single state, and S5 and S6 as a single state, and S7 and S8 as a single state. So you end up with just 4 states by this kind of definition. So that seems fine until you realize that there exists a policy which can reach S7 100% of the time. And so if you alias everything according to this kind of definition, the maximum probability that you can reach S7 is going to be 0.5, right? Because if you don't know whether or not you're in S3 or S4, well, if you don't know whether or not you're in S1 or S2, you're going to go to either S3 or S4 or S5 or S6, and then you just have a 50% chance of being able to reach S7. This is slightly delicate, but if you want to be able to reach S7 perfectly, then you didn't realize that you're in S1, and S1 is distinct from S2. And then if you're in S1, you want to take action 1 and then action 1. Well, if you're in S2, you want to take action 2 and then action 2. So this definition of state is not robust to this kind of later revelation of a difference in dynamics. And then another definition of state which comes up is by simulation. And the essential idea here is that you're going to kind of alias states which have the same dynamics and reward structure. So this is statistically intractable to learn. There was a paper recently where they discussed this in the appendix. So I have references at the end that we'll get to. Okay, so this is challenging. So now the question is, can we discover something which does work? And I'm going to start by defining a really hard reinforcement learning problem, something that we define for ourselves to kind of shape what we're aiming for. And hopefully it will help you understand what we're aiming for as well. So we're going to start in two different possible start states. There'll be 50% chance of each. And then each of these states will have one action going out, which 50-50 leads to 2 next states, right? So the fact that that the transition is stochastic means that you must kind of observe where you must make an observation in order to decide what the right next step is going to be. So it has to be a closed loop solution in a control theory sense, right? And then while one of the actions leads to this 50-50 choice, the other 9 actions are going to lead you to a bad state. And we'll even give you a little bit of reward for going into the bad state. So that's challenging for myopic reinforcement learning algorithms. And then we're going to repeat this 100 times. And why 100? Well, 100 gives you a really nice number, which is Google. The odds of successfully solving this problem are going to be 1 in Google, which is greater than the predicted number of atoms in the universe. So if you want to randomly guess in order to achieve this large reward at the end, it's going to take a very, very long time. Okay, so this is a super challenging problem. If you are quite knowledgeable about the literature, you know that this problem is actually quite solvable, given what we know right now, because MDP learning approaches can just churn through and discover exactly where to go. And so we need to make it one more step to make it something extra challenging. So instead of telling you the state, I'm just going to tell you an observation which is derived from the state. These are 4 examples of observations which are derived from the state. We have some stochastic process which creates these observations. And now you can kind of tell that there's nothing which is really strongly identifying about, there's no like individual dimension which says, oh, this is state 3. It's kind of some complex combination of these, which can tell you what the underlying state is. And now suddenly these MDP learning approaches just kind of fall over because they have no mechanism to generalize, which is an essential aspect to solving this problem effectively. Okay, so we have an algorithm called Homer, which does solve this problem, and I'll go through that in a moment. But I want to kind of go through what this looks like. So we have 100 time steps. So you can see the 100 time steps from left to right here. And the best baseline we could find was using PPO as an optimization algorithm, and RND, random network distillation, to help address exploration. And what you can see here is that even for the very best trajectory of the best baseline, it's still relatively early, falls into the bad state, and there's no escaping the bad state. It just stays in the bad state until the end. Well, with Homer, you know, it chugs along and it eventually learns and it gets the gold, and it essentially succeeds every time. So that's obviously a large difference in performance. You can also ask, if you average over all the trajectories that are taken, there's, I would guess, 1 million trajectories taken. I'd have to look at the data paper again. Then you can ask, where do these trajectories go? And you can see that the PPO and RND approach is falling into the bad state and just getting stuck there all the time, while the Homer approach is exploring over everything and achieving good coverage. Okay, so I'd like to stop and ask if there are any questions so far.
Let's see. So we do have one question from Evgeny. The question is, can you provide an intuition on why it is intractable to learn the biosimulation abstraction?
Yeah. I think the basic issue, so we're thinking about states which have the same entrance and exit dynamics. And the number of samples required in order to know that the state has the same entrance and exit dynamics is at least proportional to the number of states, and quite possibly more than that. So if we're thinking of our state as being an observation in the sense that I'm talking about here, it takes forever. You have to get an enormous number of samples in order to be able to be sure that two different observations are the same. So I think we need to be very careful about the word state. It can be used in two different ways, at least two different ways. One way is to describe your observation in a reinforcement learning setting. And one way is to describe the information required in order to make good decisions. So I'm thinking about situations here where the latent state is simple and the observation state is very complex. So if you're trying to do biosimulation directly, you need to figure out that different observation states can be aliased so that you can aggregate them so as to create essentially the latent state. And that just takes quite a while.
Thank you. And the next question is from Shaban. The question is, does a similar issue arise in goal-reaching problems in continuous states?
Oh yeah, certainly in continuous states, a similar issue arises, but if you have continuous states, then what I'm talking about right now is not going to work that well because I'm talking about discrete states. But we'll get back to continuous states a little bit later in this talk.
Thank you. Those are all the questions.
Okay, cool. Okay, so we have this hard reinforcement learning problem where it's kind of exercising all three aspects. And we have this algorithm, Homer, which solves it pretty effectively. And now I want to go through what this algorithm does exactly. So Homer is an algorithm that starts from knowing nothing and then begins to learn how to behave at larger and larger horizons. So although the episodes that you're getting are all linked to 100, it's going to start trying to learn what to do at the first time step. And then, okay, so what it does at each time step breaks down into 3 different high-level things. The first part is, so initially we know nothing, but we're just going to act randomly. Later, I claim that we're going to learn the latent state of previous time steps. And furthermore, we're going to have a homing policy, that's this phi sub s, which can reach that latent state with high probability. So we'll need to be able to satisfy that inductively in order for this to work. So for each of these latent states that are reachable with h minus 1, little h minus 1 steps, we're going to use a homing policy to find an observation at h minus 1, and then we're going to act randomly, and then we're going to make our next observation. So this is a way to gather information. So this is an exploration process. We're gathering the x, the a, and the x prime. Okay, so that's it's useful. Now we need to do state abstraction. So how are we going to do state abstraction? Well, what we're going to do is we're going to create a regression problem, which is essentially trying to predict whether or not a sequence of x, a, and x prime is causal or acausal. So there'll be a label of 1 when it's causal and a label of 0 when it's acausal. And now we're going to do something a little bit complex. So it's not just an arbitrary regressor that we're using. We're going to use a regressor which has a bottleneck in it. So we have the form of this regressor is going to be, so P is essentially just a little lookup table, but phi can be a very complex function. It could be like a ResNet, which looks at images. It's going to boil all that information down into one of a few discrete values, which are then given to the lookup table, which takes the discrete values that phi outputs and the action, and then makes a prediction of what y should be based upon these discrete values. Okay, so this is the state abstraction problem we're trying to solve, this contrastive learning problem. And then once we have this phi learned, we're going to say, okay, so for each value of phi, I'm going to learn a policy which maximizes the chance of reaching that value of phi, of after h time steps, saying phi of x prime equals s. Okay, so I'm not going to go into detail about how this is possible, but since we know how to reach all the intermediate earlier states inductively, it turns out this is relatively easy to solve. The particular algorithm which we use in the paper is policy search by dynamic programming, which is essentially just an inductive application of contextual bandit learning. So you already know how to reach the previous, the time step h minus 1 states. You reach those, you act randomly. Some of those with high probability are going to end in x prime, for which phi of x prime equals s. That gives you reward 1. Your reward's not too sparse. Now you can learn what to do with the last time step, and then you can go back to the second to last time step, and then the third, and the fourth, and so forth. Okay, so we're going to repeat this process of exploration, abstraction, and learning a homing policy over and over again for different time horizons. And then at the end, we're just going to return the set of homing policies. Or if you have an external reward, you can, again, use these PSDP approaches to be able to quickly learn a good policy. Okay, so that's a fun algorithm, because it's not just explore or exploit, it's explore, abstract, and home. Okay, and now you can go beyond this. You can look at the traces that you observe, and you can look at the value of phi of x, phi applied to your observation along these traces, and you can recover the underlying latent state space. So we did this, and this is what we observed for that problem. And everything is as expected, except for one time step where the state collapsed. And at first we thought this was a mistake, but it turns out it's not a mistake. The reason why it's not a mistake is because the action, which was the good action for the two different good states at this time step, ended up being the same just by random chance. So it's fine to collapse. It's fine to call this just a single state. Okay, so it was unsurprising to us that this algorithm worked on the problem that we created, because we actually proved that it would work. Essentially, so at a high level, we proved that if your observations are rich enough to identify the underlying state, and your learning is good enough to achieve good performance, so like think of a deep learning algorithm which is highly flexible, like then you can find this covering set of policies which will let you home to every individual latent state. And then once you have the covering set of policies, it's very straightforward to prove that you can learn to optimize any reward function that you might care about. So I want to unpack that a little bit more, just to be a little bit more precise. The model that we're thinking about is a block MDP. And in a block MDP, you have states and actions in a transition matrix, just as in a normal markup decision process. But you also have an observation process, Q, over your observations given the underlying latent state. And now the key distinction, or the key extra requirement that we're imposing over a POMDP is that X is disjoint over S. So there exists some function which, given X, can decode the latent state S. So I like to think about images, which are, maybe an image is sufficiently rich to tell you exactly where it was taken, but you may not know in advance exactly what that decoding process should be. Okay, so this is kind of the key model that we're working in to prove things. And then we're also assuming realizability. So for every bottleneck regression problem, the regressor class can find the best answer across all possible functions. And when we're trying to learn these homing policies, each contextual bandit learning problem that we're creating can be solved essentially perfectly. So these are strong assumptions. Obviously, they're better met by by richer function classes, but our results are going to degrade to some extent with the richness of the function class that we're working with. So given the realizability and given the block MDP assumption, we can see the theorem. The theorem is that for any block MDP, as long as you can visit the state with a reasonably high probability, if the learning oracles work well, so you achieve your realizability, and they return an empirical optimum so they return the best regressor on the empirical data set that you create, or the best contextual bandit solution on the empirical data set that you create, Then with high probability, you can learn an epsilon optimal policy in a number of samples, which is reasonable at a high level. So you're going to have a polynomial dependence on the number of actions and the number of latent states. You'll have a dependence on maybe the log of the number of functions in your regressor class, or the log of the number of policies in your contextual bandit class. And then you'll have a polynomial dependence on the time horizon and exactly how good your final policy is, and on the log of the probability that things fail. Okay, so I think I should ask if there are any questions here, because we've gone through 2 pretty detailed slides.
So are there any questions about this first? So I guess there was just one question on what the 1 means in the algorithm, whether it's the reward. And
no, this is not the reward here. This is this is a fictitious label that you create, which indicates that this is the causal sequence of XA and X prime. While the 0 here is just another label you create, which indicates that the X prime is not created from a causal process. So we're taking our reinforcement learning problem, and we're transforming it into 2 kinds of problems. One of them is a regressor problem, right here, where there's a little bit of extra constraint on the form of the regressor, and then more general contextual bandit learning in the process of trying to find these homing policies.
Thank you. Okay, so we have another question from Shabam. How are you defining a given action leading? How are you defining, I guess, a given action leading to a causal observation?
Yeah, so when we're gathering information, we're homing to some particular state using our homing policy that we learned. That gives us our X. We're choosing the action uniform randomly, and then we're observing the X prime. So the A is just created according to this process.
Thank you. We have a few more questions actually. So the next question is from Ramana. So when the label is 0, I think the triplets, right, XA, X prime is a random tuple where, okay, so that's actually responding to the previous question, never mind. Next question is from Arun. Is there an intuition on why this contrasted dynamics prediction leads to fixed latent spaces?
Sorry, can you repeat the last bit again?
Yeah. Is there an intuition on why this contrasted dynamics prediction leads to good latent spaces?
Yeah. I mean, I find it hard to give a general intuition, but we could go back to the counterexample and we could discuss what happens there. Right, so let's think about this counterexample. So if we're in S1 or S2, and then we take action 1, we'll end up in S3 or S4. So if you substitute in a random other observed observation from this time step, you might substitute in, so suppose we're in S1 and we take A1 and we see it S3. We might substitute in S4 or S5 or S6 for the acausal the sequences. So if you substitute in S4, then you can observe that S1 followed by A1 leading to S4 is acausal because the label is 0. So the S1, A1, S4 is only associated with label 0, while S1, A1, S3 is associated with label 1. So the learning algorithm the regression algorithm can look at this information and discover that and predict effectively that S1, A1, S4 is acausal, while S1, A1, S3 is causal. So that's kind of the key way that you get around this counterexample, using the contrastive learning problem in Homer.
Thank you. Let's see. Yeah, I think those are all the questions.
Okay. Okay, so this is, we could finish here, and I could say, look, it is possible to discover latent state space, to provably discover a latent state space, and it allows you to solve reinforcement learning problems that nobody else could solve. That alone, I think, is not sufficient, because the kind of reinforcement learning problem that we solved is pretty artificial. And there may, in fact, be real-world problems where you need this technique, but there are also a large number of different reinforcement learning problems where this technique is going to break down in various ways. And so, since we worked out this Homer algorithm, we've also been thinking about extensions of this approach in various ways. So, one other kind of natural structure is to suppose that the transition matrix in your observation space is low rank. So so maybe X is a picture, X prime is a different picture. You have some function phi which takes a picture and an action and maps it into maybe a 100-dimensional vector, and then you have some other function mu, which takes another picture and maps it into a 100-dimensional vector, and that's going to, when you take the dot product, that's going to define the entry in your transition matrix. Okay, so this is kind of natural. We know some things about this kind of structure. We know from an earlier paper in this. Okay, so let me back up. First of all, we know this generalizes block MDP because you can express any block MDP of the sort that I just described as a transition matrix of low rank, where the rank is the number of states. We know that this is statistically tractable to solve with another paper from a few years ago about low Bellman rank. And then there's also a paper recently which shows it's computationally tractable to solve when phi is known. Okay, so can we actually, if we don't know phi, can we actually effectively discover this sort of latent state structure? So now, just to be clear, our definition of latent state has changed. It's no longer just an enumeration of a set. It's now kind of a real vector of not too large a length. But nevertheless, we can call this a state. It may give us the information that we need in order to make decisions about what to do, and then we can build from there. And it seems that the answer is yes. So there's this Flambe algorithm, which is on arXiv now. And it's solving a different kind of prediction problem. Essentially, you're maximizing the log loss of this dot product. And when you're trying to learn the representation, so again, phi and mu here can be very complex. And then when you're trying to explore, you're trying to essentially maximize sort of the range of different phi of xa's that you can reach as far as the planning purpose goes. Okay, so this is one generalization, which is interesting, and you can prove that this will work, but we can go on. So what if the latent space has linear dynamics? That's kind of a different question. So the natural version of this is something where you have, think of a rocket ship where you have your location in space, you have your evolution through time, which is what the A matrix does, and then you have your thrust, which is what your rocket thrust does, and then maybe you have some noise of one sort or another, and that leads to a new state, and now maybe we have a observation process. So instead of actually knowing the location of the rocket, all we get is the image of the rocket. And based upon the image of the rocket, we want to be able to learn to control the rocket. So that's kind of cool. It's a lot of physics problems have this kind of at least locally linear structure. We're thinking about globally linear here as a first step, but physicists are always trying to linearize things because that is often what the local structure just looks like. So can you do it here? It seems the answer is yes. This is a paper which is probably going to come out in archive pretty soon. I don't want to go into details. There's a more complex process here of a multi-phase algorithm where you are acting randomly for a while, using that to recover the local dynamics, using that to plan to optimize your reward, and then again learning on the trajectory of the optimized policy because you're reaching a new part of the observation space that your initial random actions did not actually observe. Okay, and now we can go another step. We can say, look, in many real-world situations, our state space is really a very combinatorial thing. So in particular, so I have a table in front of me. On this table, there are probably about 24 objects. These objects have some particular arrangement. I could rearrange my table, and I could rearrange my table over and over again, getting a different arrangement of things, and each would be different. Each would be a different state. So if I have a polynomial dependence upon the number of states, this is never going to work because the number of states is very, very large. But still, there's something simple about going on here. If I go over to my glass and I pick it up, there's only a very local change to the state of my table. So this is captured by a factored Markov decision process. The idea there is that in your latent state space, the transition matrix can be decomposed into a transition matrix for each individual factor, where that factor depends upon only very local things. So that dependence upon only local things is a natural structure to the world, and you might hope that it's possible to discover these latent state spaces, these combinatorial or factorizable latent state spaces. So we've been thinking about this, and yeah, it's a little bit less clear how high a quality of solution is possible here. The approaches that we have so far require more assumptions than we want, but still it seems we can do something, and that's kind of interesting. It suggests that maybe this approach can be applied to much more complex settings than you would imagine if you're just enumerating states. Okay, so I've kind of gone through a lexicon of different projects related to recovering these latent state spaces. If we can recover these latent state spaces, then we can start solving these reinforcement learning problems much more tractably than we might be able to right now. I mean, I think often right now, people are essentially brute forcing the exploration problem. They use relatively simplistic exploration approaches that maybe eventually work, but eventually might mean 10 to the 100. So it's not actually practical for some problems, and for others, it's just incredibly inefficient. So if we can discover these latent state spaces, then maybe it's possible to succeed in a much more general fashion, much more efficiently than existing algorithms can. And so there's many different concerns, complaints, issues that you can have with this solution. And I think that's very welcome at this stage, because we're just starting a research. This is a research project. We're not yet ready to say we fully understand how to do things, but I wanted to kind of go through what I think are important questions to think about if you're interested in working on this research project as well. So there's a substantial gap between theoretically tractable and practically tractable. So that's something to be concerned about, and trying to figure out how to make things be the most elegant and efficient solution possible, I think is very important for these approaches to really flying well. Right now, we're developing a lexicon of these state-deriving learning processes. It's not super clear yet what the scope of that lexicon should be or could be. It'd be interesting to know that. There's sort of some qualitative differences between these different state-deriving learning processes. And again, we don't fully understand all the details. We're very much in our own exploration and discovery phase of this process. And then the last thing is, I think, a really important question. I think often we have an intuition that latent state discovery can be very powerful in helping us solve these problems, but it's not entirely clear to me that every kind of latent state that we would imagine should be discoverable is discoverable. So the limits of what we can discover as far as latent state tractably are not very well understood, and I would certainly like to understand that. Okay, so these are some of the people that I've worked with on these projects. This spans multiple papers, and this is the bibliography references from the presentation. So are there other questions?
Okay, let's first thank John for the very interesting talk. We do have one question, actually, let me see, a few questions at this point. So the first question is from Shabam. The question is, how will the approach change when the latent space is high dimensional, but meaningful features are low rank?
Yeah, so if the latent space is high dimensional and the features, oh, hold on. Okay, so let me answer this two ways. So if the features are simple, if the observations are simple and the latent space is complex, that gets very difficult. So there's some strong hardness results for POM-DPs, which have this kind of structure. Now, if the features are low rank in the sense of this, and the latent space is high dimensional, I think you still have difficulties, and that's pretty essential. So here we're thinking about the dimensionality of latent space as being something not too large, and that's fine because we kind of have a polynomial dependence upon the dimensionality because we're assuming linear dynamics. If you don't assume some sort of simplicity to the dynamics, then you easily fall into a cursive dimensionality problem, right? So think about a hypercube in this high-dimensional latent space. If every corner of that hypercube can behave in a different fashion from every other corner, so it's unconstrained by the other corners, then you just inherently have a very complex problem.
Thank you. So the next question is from Pavan. The question is, when noise is introduced, would improving the homing policy help? Or the previous stage of predicting the causal sequence needs to be looked at?
When noise is introduced, I didn't quite understand that one. Say it again.
So when noise is introduced, would improving the homing policy help, or will we need to, I guess, look at the previous stage of predicting the causal sequence? I guess it's asking the distinction between the like learning of phi versus the homing policy when noise is introduced.
So you're taking random actions here, and that's just to achieve a good exploration of possibilities. And you're randomly choosing how you perturb, how you create acausal examples, so that you don't accidentally create causal examples, basically. So some of the x primes might in fact be causal, but you don't know that. So as long as a substantial fraction of the x primes are acausal, taking a uniform random choice means you'll typically get an acausal example. And that means that the prediction process will work out. So it may be the case that sometimes the minimizer here, this p of phi, is not 0 or 1 because there is some noise introduced due to the x prime being sometimes causal, even though we label it as acausal. That's fine as far as the theory goes. That's fine as far as practice goes, although it makes the learning process just a little bit harder.
Thank you. Okay, so the next question is would it be right to say that Homer's success would depend to a large degree on how noisy Q of x given S is?
I believe the answer is yes. So you're asking about this Q of x given S here. So as far as the theory goes, we are relying upon x being disjoint over the states, right? So that means that there exists somewhere a function in which given x can tell you what the S is. You don't know that function, but you have to discover something about it. If it's the case that x can be generated by multiple underlying states, then the theory just breaks down. Now, how essential is it is a little bit less clear. It seems plausible that, so I've seen some memory-related papers which suggest that it may be possible to extend these results to situations where the x has kind of mild forms of ambiguity. And empirically, the process that we used when we're playing around with this problem does actually generate ambiguity with some small probability. So the algorithm seems to apply a bit more generally than the theory would suggest.
Okay, thank you. The next question is from Evgeny, which is a high-level question. So there's a lot of recent work on learning causal/disentangle latent representations. Do you think that is a tractable problem to solve?
So yes, in the sense that we are learning a causal representation here, right? I mean, we actually discover the latent state space. And so that is tractable, at least for block MDB problems. And this is creating a disentangled representation in the sense that we know sort of what the key, well, okay, so I think disentangling actually has to do with this problem here, right? So disentangling is usually used to describe the situation where you have multiple factors and they can kind of vary independently. So that it corresponds to a factor representation of the state space. So here, it's clear we can do something. I'm confident of that. It's not yet clear how general that is. So for causal representations, the answer is certainly yes. For disentanglement, at least as far as the foundations go, we're still working on that, and I don't think we have the best answer yet.
Thank you. Oh, by the way, if Jenny, you have any follow-up comments, feel free to unmute. I guess not. Okay. So the next question is from Puyan Jamshidi. The question is, let's see. So I was wondering how we can go after state driving learning process. Is physics informed way, i.e. augmenting the learning with physical models of the environments and mechanisms by which we interact with the environment could be relevant or promising? Yeah, I suppose it's just asking for your views on.
Yeah, so I think that it's fairly related to this question here. Right. So there's a relatively small lexicon of sort of physics, common physics models. And here we're trying to address one of them, and we're getting a positive answer. If we can work through this lexicon of standard physics models, then, and we can get a positive answer for each, and then we can kind of compose those answers into some sort of general algorithm that can discover which answer is relevant to an individual problem. Then I think we could be in a very interesting place, because then we could have an algorithm that, I like to think about sort of a Mr. Potato Head robotics, right? So you take some sensors and take some actuators and you slap them together and you give them a processor, and then you just let it go. So you do no modeling, you just let it run around the world. It bumps into things. You probably want to do this with a small robot rather than a large one. And it discovers its latent state space, and it learns to navigate around. So this might even be useful if it's done on a Roomba. So that process of kind of discovering the world and through exploration, it seems like it may be possible if we can learn this lexicon of natural physics models.
Thank you. Puyan, do you have any follow-up comments?
No, that answers well. But I was wondering, like this physical model that you're talking about in this particular case, this is more specifically related to the states, right? And the transition between the states, which is useful. And the question that you mentioned, is it only really related to the states, or could be even beyond that? Because part of this is somehow related to this mechanism that we interact with the environment. It's not only about the state of the system itself, right? Some part of it is related to these mechanisms, and this could really affect the way how the states of the system would transition, right? Is that like learning or augmenting some understanding of these mechanism could be also useful, or like your question was somehow constraint to the states?
So I guess when I'm thinking about latent states, I'm particularly thinking about the world as having a definition of latent states, and we're just trying to discover what that definition is based upon our observations and our learning processes.
Right, right.
Great, thank you. Are there any other questions? Okay, if there are no more questions, that concludes today's seminar. Let's thank John again for the very thought-provoking talk.
Thank you all. Hope this was interesting.